I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on antenna parameters for the course Antennas and Wave Propagation. So let us discuss the video. We are going to see the contents of this video is the first we see recall. We'll recall some of the antenna parameters what we discussed in the previous video. Next we will see another important parameters of antenna and applications. Some so in the previous video we have seen so many important antenna parameters like radiation intensity, which is the power radiated per unit solid angle, radiation pattern as the graphical representation of antenna as a direction, and gain, directivity, important antenna characteristics which defines the performance of the antenna, front to back ratio, which is the radiated power in forward direction to the backward directions, effective length of the antenna, and radiation resistance. So now in today's video we will discuss the need of understanding the antenna parameters, which is the empathy part. So antenna parameters specify how effectively an antenna transmits or receives electromagnetic waves, and which will be useful for engineers to design, analyze and optimize antenna systems for specific applications. So the first parameter we are going to see is antenna impedance. So understanding the challenge. So for in antenna design, matching the antenna impedance to transmission line, which ensures maximum power transfer and provide minimal reflections. So the antenna impedance is specified by the letter ZA, and which is equal to RA plus JXA. Here RA is resistance of the antenna, which is again classified into loss resistance and radiation resistance. Here the imaginary part of antenna impedance is denoted as XA, which is the reactance or energy storage. So the optimal value of ZA is equal to the characteristic impedance Z0. Typically it is 50 ohms. So next parameter is wave polarization. So polarization is known as the orientation of electromagnetic wave. That is, it specify the direction of electric field. So in which direction the electric field is there, which defines the polarization of the given wave. So based on electric field orientation, there are three types of polarizations. One is linear polarization, second type is circular polarization, third type is elliptical polarization. In linear polarization, we can further classify it into uh, uh, two types. One is the horizontal polarization and another one is vertical polarization. And circular polarization is the type where EX, EY components are equal, and the third case is elliptical polarization. So now the next is the defined part. We are going to see the beam width of the antenna, which is taken from the radiation pattern of the main lobe. So in the main lobe only, always these parameter is measured. So there are two types of beam width. One is called half power beam width. So in the half power beam width, it is the angular width between the 2 points called as half power points, at which the power is radiated power is half of the maximum value, or it is minus 3 dB down from the maximum value. So its applications, this will be very useful for radar systems, require narrow beamwidth for precise target location. And if narrower the beam, we can say that the antenna directivity is high, which is the preferred characteristic. And half power beamwidth for aperture antenna, it's approximately 70° lambda by D, and E plane H plane beamwidth can. And next is the antenna temperature. So in the antenna temperature, it is defined as the equivalent temperature of resistor producing the same noise power as the antenna receives. So the contributing sources of this antenna temperature is cosmic background, ground radiation, man-made interference, and atmospheric absorption. So this will be vary, and its formula is Ta is equal to integral of Tb of theta comma phi, G of theta comma phi, d ohm divided by G of theta comma phi. So the Friis transmission equation is the next parameter. It is an important formula which gives the received power, which is given by PR is equal to PT GT GR multiplied by lambda by 4 pi R the whole square. So here PT is the transmitted power, which is the input power given to the transmitting antenna in watts, and GT GR are antenna gains in terms of the decibels, and lambda is the wavelength, operating wavelength in C per F. So here C is the velocity of light, F is the frequency of the operation of the antenna, and distance is separation between the antennas given by R, and the path loss is given by lambda by 4 pi R the whole square. And now coming to the real world applications, are this will be useful in antennas are useful in wireless communications, where 5G networks utilizes beam forming with control impedance, which matches the polarization density for enhanced coverage. And in order to study these antenna parameters, we can understand how the antenna can be useful in various applications. For example, this will be useful in satellite systems. Low antenna temperature is critical for deep space reception, and here the Friis transmission formula guides link budget design. Next is the radar technology. Narrow beamwidth enables precise target tracking, and here also we need bandwidth support for frequency agility. And radio astronomy also, these parameters will be useful because we are always prefer ultra low noise temperature antennas. And summary, so far we have studied impedance, antenna impedance, polarization, beam width, and also bandwidth. So by learning all these parameters, we can easily design the antennas, and this will be useful for antenna design engineers to optimize the performance of the antenna for specific applications. References. Thank you.